here I have a CD case representing a part of an infinite plane. I can't handle an infinite plane. I could handle the infinite line, but an infinite plane is a bit much. Okay, now, what's the direction of the electric field if this infinite plane, if this is part of an infinite plane that contains a uniform charge density, let's say of 3 microcoulombs per square meter? Okay? So here's the plane. Let's just put the plane flat for a minute. What should be the direction of the electric field coming off of this plane if the charge is spread out completely uniformly over the entire plane? Well, there's a symmetry involved. If I rotate the plane, I still have an infinite plane, and that shouldn't make any difference in the direction of the field. What direction is independent of rotation of this plane about an axis perpendicular to the plane? Okay, so we put an axis perpendicular to the plane, rotate the plane about that axis. I'm wobbling it a little bit, but you can imagine that we have a uniform rotation. Well, the only direction is the perpendicular direction. Okay, so that as we rotate the plane, the electric field doesn't change. That perpendicular direction is unchanging. If the direction is not perpendicular, okay, now let's look at this one. As I rotate, the direction of the electric field keeps changing. Rotating the plane still leaves me a plane with the same charge density and the same normal vector, the same perpendicular axis, so that obviously this can't be. Also, if the field vector has different values at 2 different points, then one would be longer, one would be shorter. If we rotate about an axis between those points 180 degrees, the longer would switch with the shorter. And that couldn't be either. So we conclude that the electric field has to be uniform and perpendicular to the plane. Now, if we have a finite plane, like one of these jewel cases, then that is more or less true. What we just said is more or less true of this plane also, as long as we don't get too near the edges and as long as we don't get too far away from the plane. Okay, if the plane is here, okay, if we're at a point here very close, then from that perspective the plane is effectively infinite. Everything out here past the edges doesn't make much difference anyhow. If we just cut this part out of an infinite plane and look at it from right here, look at the electric field from right here, there's not going to be much difference. Now we have to prove that mathematically, but you can accept that multivariate calculus will allow us to verify that completely. So near the plane and not too close to the edges. If we're much nearer the plane than to the edges, what we just said remains true. The field should be uniform. It shouldn't change as we move away from the plane until we get so far away from the plane that we're not very much closer to the plane than the edges. That is, if we move from here out to here, okay, let's say we're at this distance, then here's how far we are from the plane, and we're this far from the edges. There's not much difference there. We have to be much closer to the plane than to the edges for these assumptions to hold. Let's just arbitrarily say at least 100 times closer to the plane than to the edges. Now, in that situation, if sigma represents our charge density, our charge per unit area now, sigma being an area density, and if this is a section of the infinite plane, we could draw a surface consisting of a box perpendicular to the plane and passing through it, where the cross-sectional area of that box is A. We'll designate the cross-sectional area by A. The box is perfectly rectangular. All the corners, all the sides make rectangles, so that the ends of the box also have area A. Since the electric field is perpendicular to the plane, the only place the electric field can get out of the box is at the ends. So that the electric field through the ends will be, well, the electric field only escapes through the ends. Forget that sentence that I started. It wasn't a good sentence. Now, if the electric field exits only through the ends of the plane, then if we know the flux, which we're going to be able to find, that flux will have to pass through the ends. And that flux, or the electric field, will be uniform on the ends, so that if we just divide the flux coming out of this rectangle by the area of its ends, which will be twice the area of one end, we're going to get the electric field. So let's just see how this works. The charge enclosed by the box is what? Well, it's an area A of the plate, the infinite plane here, that's enclosed by the box. So we multiply the charge density, charge per area, by that area A. The charge is sigma times A. The flux is therefore 4 pi k q, or 4 pi k sigma A. The flux is through the ends of the box. The ends have total area 2A. And the flux is uniform and perpendicular to those ends because it's unchanging in the vicinity of the plates, and it's perpendicular to the surface, and the box is perpendicular to the surface. So that the electric field times the area is the flux, which is 4 pi k sigma A. Electric field times the total area. The total area of the ends is 2A. So we take the equation electric field times 2A equals 4 pi k sigma A, and we see that E is 2 pi k sigma. Now, if we take two of these plates and put them close together at some preferably uniform spacing, okay, and let's say that these kind of hard. We can get a uniform spacing. We might as well demonstrate how that might be done. Okay, we're going to get them real close together. We're going to separate them by this single sheet of paper. Okay, now the plates are at a nice uniform distance of about a 10,000th of a meter apart. Now you can't really see the space in between them if I do that, so I'm going to leave them like this. We're going to pretend at this distance the spacing is the same. If these are two conductors, and if I attach a wire from this plate around to this plate with nothing in between, then if I put a generator in that circuit, wire to generator and around to this plate, I can pump electrons off of this plate and onto this. Or depending on the nature of the material, I might pump electrons one direction and positive charge carriers in the other direction. Now, in doing so, I end up with a positive charge in one plate and an equal negative charge on the other. That charge will be uniformly distributed because on a conductor the charges get as far away from each other as they can. So on each conductor, on each plate which is a conductor, they're going to be as far away from each other as they can be, which means they're going to be uniformly distributed. As a result, I'm going to have some positive charge density on one plate and a negative charge density on the other. Now, if this line represents one plate and this line represents the other, here's my situation. Let's say that my color coding really is bad here. From the red plate, which generally indicates positive, the vectors ought to be moving away, but I've confused that. I think I wasn't thinking of it when I did this, actually. But let's say that the black plate is positive and the red plate is negative. That's just the opposite of the way it should be. But let's take it for right now as the way it is for the situation. Then from the positive plate we'll have an electric field 2 pi k sigma going away from the plate, and that field will be uniform except very near the edges of the plate. And on this plate, the negative plate will have an electric field going toward the plate. Now, in between the plates, that means the electric fields are going to end up parallel, away from the first plate and toward the second, or the same direction. So we have the fields reinforcing. We have a 2 pi k sigma and a negative 2 pi k sigma. But in between the plates, they have the same direction, giving us a field of magnitude 4 pi k sigma. Outside the plates, these fields will be more or less equal and opposite, and they'll cancel out, and we won't even have an electric field outside the plates. We've got this strong electric field confined between the plates. This setup is called a capacitor. That's what we mean by a capacitor. And we'll investigate the details of this situation and how the voltage relates to the separation of the plates and so forth later.